So the first rule they've said to you is that our function, when we go to graph it, okay, and what this is we have almost like type of reciprocal, we have a division of two functions, okay? So p at x is one of our functions and q at x is another. So we could have split these, but they actually only represent one function, or f at x. This one's talking about a hole in a function when we go to graph it. So if our inequality, or what usually causes an asymptote, where zeros, if a, whatever number that is, causes 0 to occur on the top and the bottom, okay, it's going to put a hole in our graph. So, for instance, question 1b, let's talk about these. Okay, question 1b, we have y equals x squared minus 9 divided by x minus 3. Okay. Now, in order to find our horizontal and vertical asymptotes, we need to factor wherever we can and also set tops and bottoms of the equations equal to 0. So in other words, I know that I would get an inequality or something that wouldn't exist if this was equal to 0. And same with if this was equal to 0, right? So I'm going to split them, but I also need the factor form of the top one, okay? Because I got to figure out what values are x. So I'm going to factor the top of this function. Do you know what it'll be? Good. Okay. X minus 3. So here's where we can start to split our function. Okay. We look at this. I'm going to set the top. We'll do the top in blue. Okay. Top will be done in blue. So it actually is two functions. 0 is equal to x minus 3, and 0 is equal to x plus 3. And our bottom, we'll do in red, 0 equal to x minus 3. And really, actually, these cannot equal. Okay, so we got to figure out what numbers these can't equal. Right? Otherwise, we're going to end up with either zeros or non-existent numbers. So in our first one, we get x can't be 3. Our other one, we get x can't be negative 3. And on our bottom, we get x can't be positive 3. Okay? If we look at this, there's a similarity between this one and this one. Our top and our bottom, if I were to plug the number 3 in, is going to cause a 0 to occur on the top and bottom of this function. And just to prove that, we'll get y is equal to x squared minus 9 minus 3. So this was our original function. Let's say f at x, so we're going to replace y with f at x is 3. Okay? So if f is 3, it's equal to 3 squared minus 9 over 3 minus 3. What are we going to get on top and bottom? 3 squared is 9 minus 9 divided by 3 minus 3. What will we get? Over. Great. Okay. So let's talk about graphing it then. When we go back to it, we're going to have to figure out what has happened to this number here. Okay. And if you look, we get 2 and 4 is our whole. So we go to graph this when x is 2. Let's put a graph. We knew that because the same x value is going to cause 0 and 0. We're going to end up with a hole in the graph. We just kind of got to figure out where it's going to be. So your teacher showed you it this way. Okay. So your teacher has shown you limits. Okay. And the way she denotes them, she goes, okay, so what we're going to do here is we're going to find the limit of this as x approaches the infinite. Okay. So what she does, she takes the highest degree variable. Okay. So in this case, our highest degree variable is x squared. Okay. So what I'm going to do is I'm actually going to divide each of the terms in this equation, x squared, divided by x squared, minus 9 divided by x squared, all divided by x divided by x squared, minus 3 divided by, I want to do these in red so you understand, divided by x squared. Just trying to make sense of this a little more. Okay. So she's divided every term by x squared, and then in her division, she equates anything we can. Okay. So we're going to simplify these things now. So for instance, x squared divided by x squared gives us what as a value?
0. Or like, we cancel out.
It's the same number.
Yeah.
It's like 5 divided by 5. What's that give us?
Like
1. Okay. I can't simplify 9 divided by x squared. And we assume the infinite is almost like plugging in the number 0. So it's going to make it disappear. Okay. We'll do that in a second. In our other one we can simplify. We'll end up with 1 over x. All right. And again, we can't simplify this. X 3 divided by x squared. So in this case, the infinite, if x is infinity, okay, so if x is infinity, what that means is we would be replacing our x's with infinity. They're going to completely cancel out whatever term there is. Okay, so the idea here is we get 1 minus 9 divided by infinity. Well, that's going to be so minuscule, the number, it's not going to matter. It's essentially a 0, we'll call it for now, okay? Divided by 1 divided by infinity. Okay, sorry, this is infinity squared, but it's not going to change infinity. It's still going to be infinite, okay? Minus 3 over, again, technically infinity squared. We'll put the squares in just for you, okay? So you see the transition of what we've done. We've replaced all our x's with the infinite number, okay? We're saying as x approaches infinity. Now what infinity does is, we're going to say, it essentially causes zeros, okay? So what ends up happening is I have 1 minus, 9 divided by infinity is going to be like a 0, okay? And we're going to have 0, subtract 0, okay?
Yeah.
So our final number is 1 over 0, okay? Which is what?
1.
We can't actually divide anything. Okay? This is non-existent because we're 1 over 0, so it's non-existent. In other words, again goes with our theory of causing a hole in the graph. Okay? So when we do finally go to graph this, we knew that x could not be the number 3. Okay? So we go to graph that. What that means is when x is 3, which is right along this line here. Okay, I'm just going to draw a dotted line wherever it crosses 3. Wherever our function crosses 3, that's where we're going to have a hole in the graph. Okay. Now, if you look at 1, what they're trying to get you to do is refer to these graphs here, and they're trying to get you to figure out which of these graphs represents which of these equations. When we look at graph C has a hole in it at x is 1, 2, 3. Right at x is 3. Okay. And it's actually, I believe this is going up by 2 in terms of your y-intercept. So 3, I think 9, here we go. We have a hole in the graph, if you look at it. So it has a graph roughly like this, and then at 3, it's non-existent. Now I know I've exaggerated this hole, and then continues again. Okay? So we've exaggerated the hole, but that's where the graph doesn't exist. Alright. Another rule that they've shown us in the book is if your function, and again we have p at x and q at x, right? As a horizontal asymptote only when the degree, oh sorry, I'm reading the wrong one. As a vertical asymptote, x is equal to a, same idea as before. But in this one, p at a and q at a, p at a is some number, q at a equals 0. So at the bottom of this is 0, then we have a vertical asymptote, okay? And we have to find what the vertical asymptote is when x is equal to that. So we'll go back to question 1a. So 1a in your book, we're just going to refer to the question like this. We have y is equal to negative 1 over x minus 3, okay? Now remember this rule. Again, we're going to check, first of all, that where our vertical asymptotes are, okay? Now the variable is only on the bottom, so we got to set the bottom of this equation equal to 0. So we'll get x minus 3 equals 0. X cannot be the number 3. So right away we know we're going to have a vertical asymptote at x is 3. Okay. Now she wants to find a horizontal asymptote. We take the same question, okay, where we had y was equal to negative 1 over x minus 3, and we set it to a limit, or a limit as x is approaching the infinite number, okay, and we divide each of these by the highest degree variable, okay, so we end up with negative 1 divided by x divided by x divided by x and 3 divided by x, okay? So same idea. Now, technically I replace my 1's, I replace my x's with infinity, right? Okay, divided by, here we got infinity divided by infinity, or x divided by x. What number is that going to give us? 1, okay? And this one, 3 over infinity. Whenever we're dividing a constant number by infinity, it's just going to essentially be 0. So we end up with 0 over 1 minus 0. What do we get?
1 over 0 over 1.
Which is? Do you know what it is when you divide it? Let's get a calculator. So this makes sense to you, okay? 0 divided by 1 equals?
0.
Yeah. So your horizontal asymptote is at 0. So let's go make sense to graphing this now, okay? So when we go to graph this, where did we say our vertical asymptote was?
3.
That's right. So at the number 3, we have our vertical asymptote. And our horizontal asymptote was at 0. So when we're graphing this, we know we're going to have some function that roughly looks like this. Goes down, comes up, and comes up, and across. Okay? So we've made our horizontal asymptote. You know, that's where y is equal to 0. And our vertical asymptote is when x is equal to 3. Which are the two things we found. Okay, so if we quickly look at this, we know that we're not going to run into the first example we had, where the number on the top and the bottom is going to be 0 and 0. We know that's not going to happen. We know this is to the second degree, this function. Okay.
Yeah.
And we're going to have to find out where this is going to be, where we're going to end up with an asymptote of this question. Okay. So let's talk about how we would set this up. What would I do in order to find the asymptote?
You have to.
So technically what this equation says, because even though it's squared, is y is equal to 1 over x plus 3 times x plus 3. So I would set both of those equal to 0. The only reason I only need to do it once, though, is because it's the exact same function. And we're going to find out that it's the same thing. So x cannot be negative 3. X cannot be negative 3. Okay, so if x is negative 3, we're going to end up with our asymptote in this question here. Okay. So we know we have a asymptote of negative 3. The only thing is, if you remember what we were doing yesterday, this is squared on the bottom, right?
Yeah.
So in other words, we're going to probably have, it's the same asymptote. So because it's the same asymptote, this one changes the way the function is going to look. Normally, if we had two asymptotes, show it in our function. Normally when we have a squared function, we usually have, let's say, an asymptote, maybe a 4 in here, and we get some function that goes up, maybe down and around, and then across again, right? But that's when we have two different asymptotes. In this question, we only had one asymptote, and what was it at?
3.
Not just 3, but
Negative 3.
negative 3. So this asymptote was at negative 3. So essentially, it's the same idea, but this time, this function's a little different. Because it is squared, we take off and up, and it's actually going to come back down this way and across.
That's weird.
Okay? Now, I know this one's pretty different than what you're used to seeing, but that's because it's a quadratic, not quadratic, but our function itself, when we go back to it, is squared on the bottom. Okay? So If you remember the square ones, remember what I said. Normally we get something in the middle that ends up like this, so that this and this makes sense. But because we only have one vertical one, this is essentially canceled out. So we only head up and then come back down when it's square. Okay? Does that make sense?
Yep.
Okay. Now with what your teacher showed you, she wants you to find a horizontal asymptote. Okay? So this question again was written as y over x plus 3 squared, right? It'll be easier if I actually put this in the standard form for what we were doing for our limit, okay? So I'm going to turn this in the standard form. So that's our x plus 3 times x plus 3. Do you remember FOIL?
Yep.
Okay. I'm going to end up with, I know I just jumped from here to here to down here, 1 over x squared plus 6x plus 9. Does that make sense to you? Okay. Now we're going to set this up so that we have our limit as x approaches the infinite. Okay. So again, what we're used to doing, we're going to divide our terms by x. So divided by x. Sorry, not just x, but what?
X squared.
Yes, because that's the highest degree function, right?
Yep.
Good. X squared plus 6x plus 9. All divided by x squared, and x squared. Okay? So let's make sense of this. This is going to just end up as 1 divided by infinity on top over x squared divided by x squared.
1.
Okay. I can equate this a little. I can cancel out an x. So I'll end up with 6 over x. Okay. And what is that x just going to become?
Infinity.
Yeah, so let's erase that. It becomes 6 over infinite. And this becomes 9 over infinite. So whenever we're dividing by infinite, what numbers do we end up with?
0.
0 divided by 1 plus 0. What do I get?
0 over 1.
Which is equal to
0.
So what's our horizontal asymptote?
0.
If we go look at this function, we had a horizontal asymptote. That's 0, right? So this one was at x is equal to -3, and the other one was y is equal to 0. Okay, same idea with this question. First step, we need to find out where our function is non-existent. Okay?
So you have to make it equal to 0.
Yeah, we're going to set each of those equal to 0. So x minus 1 equals 0. X plus 3 equals 0. Okay? And if we look at that, we're going to end up
X cannot equal to 1. X cannot equal to -3.
So we have 2 vertical asymptotes. One's at 1, one's at -3. Now, technically this function, I'm going to write it out again. I'm going to put it in standard form at the bottom, okay? Standard form, we're going to get x squared minus x plus 3x minus 3. We're just going to simplify that. So we get y is equal to x over x squared plus 2x minus 3. Is this making sense so far? So I've changed it in standard form, right? And we want to find our horizontal asymptote. So again, y is equal to the limit x approaches infinity, x divided by x divided by, sorry, do I divide by x or x squared because it's degree? X squared plus 2x minus 3. These are all divided by x squared. Okay. So y is equal to, this becomes 1 over x. This becomes 1 plus 2 over x minus 3 over x squared. So we can quickly, I don't need to write the infinities in again, do I? So we know what's this number going to become?
0.
Yep, and this one?
0.
And this one?
0.
So we're going to get 0 over 1 plus 0 plus 0. What do we get?
0.
0.
Do I have to do that every single time?
You may get different horizontal asymptotes. Okay? So far the ones we've always end up with are 0, but you are going to need to find them. So when we go to graph this function, we knew that we had two vertical asymptotes. What were they? X couldn't be 1 and negative 3, right? So X can't be 1 and X can't be negative 3. So we have two vertical asymptotes. Negative 3 and 1. Okay. And what was our horizontal asymptote? Y couldn't be 0. So we had a horizontal asymptote here. Now, remember we had a quadratic on the bottom again, right? Is there anything special about this one? We're going to draw it. Question 2b. We're going to set the bottom equal to 0, right? We got to make sure it doesn't, it's not going to exist there. Okay. So we get 2x plus 3. Who is calling me so much? Nobody's calling me. Put that on silent. Is equal to 0. We get 2x negative 3. X cannot be negative 3 over 2. Okay, so we have a vertical asymptote at negative 1.5. Okay, horizontal asymptotes. Let's figure that out now. Same idea. This time, though, when the limit of x approaches infinity, we'll do an 8. X approaches infinity. We get 1, 2x, 3. And the highest degree of these terms is just x. So we're going to divide each of them by x. Okay? So we divide each by x. Let's see what we get here. We're going to end up with, this term is going to become what?
The first term?
Yeah, on top.
That will be 0.
0. Term on the bottom is going to become what?
2.
2. And the other one?
0.
0.
Oh,
So 2, that's different, but what happens?
It's still 0.
Yeah, we still end up at 0. Okay. So, when you're looking to graph that, you have a vertical asymptote at negative 1.5 and a horizontal asymptote at 0. Now, you wanted to find one that had... Okay, question 1c. Same idea. Now, in order to check for the rules of the very first one, technically we should be looking for the top and bottom zeros, okay? Now, a top 0 is just going to cause a function to cross at 0 there, which is fine. But it's when the top and the bottom 0 are the same that we cause holes in the function. So we should be checking for them each time. So 2 at x plus 5 equals 0, and x minus 6 equals 0. Okay? This one will end up with x equals 5 over 2. And in this one we get x is 6. So the top and the bottom 0, if you notice, are not the same. Top and the bottom 0 are not the same. So that's fine. So we know we have a vertical asymptote because it's only our bottom one that's really that important at 6. Okay. Now the other thing we want to do is set it so we have a limit, y, limit of x approaching the infinity. Here we get 2x plus 5 divided by x minus 6. And we're going to divide each of these terms by the highest degree of variable, which is just x, right? So we divide each of these terms by x. Our top one, what do we get? 2x divided by x, we get
2.
What does this term become?
0.
Over,
0.
what's x? X.
Oh, 1.
1 minus.
0.
So what do we get?
2.
2. So we have a horizontal asymptote at 2. Okay. So when we go to graph this one, this will be a little different. So horizontal asymptote. We had a vertical one. What was our vertical one? It was at 6 and a horizontal one at 2. So vertical asymptote number 6. Horizontal asymptote number 2. Okay. So when we go to draw out that function, we're going to have those two asymptotes. I just need to fix the.
I already did that stuff.
Yeah. The reason we did this is just to check if these two are the same. Because they're not, it doesn't cause a hole in the graph.
Oh,
Okay.
yeah.
Now this, it doesn't matter what that is. That's not a vertical asymptote. It's only the bottom of a fraction that causes